Alright guys, so whether you know it or not, this is actually like the second trial of me trying to take a video of myself doing this derivation because, well, I've got that cool smartboard tool that I can't figure out how to make work with audio, so until then you're going to have to deal with looking at me, which, well, sucks for you. So, today we're going to finish up doing our charge to mass ratio of an electron. And this is really important because this is how we found it out experimentally as scientists anyways. It wasn't just like, they found a charge and they found a mass and they figured out which was which. Plus, they can use this for any type of charged particle, not just an electron. So what I've got up here is I've got an electron sitting on a negatively charged plate. Because there's an accelerating voltage applied, it's going to go to the positive plate and continue into this region of magnetic field. So we're going to do a little bit of conservation of energy. If we look at it, first off, it's going to start with an accelerating voltage, which means that its electrical potential energy is going to be QV. So QV, that's going to be equal to the amount of kinetic energy it gains by the time it leaves here. If that's the case, then I know the kinetic energy is 1/2 mv squared, where the big V is for voltage and little v is for velocity. What I want to get out of this equation is velocity, because voltage is something I control, mass is something I measure, charge is something I measure, but there's no good way to get velocity. So that's something I want to cancel out later. So velocity, that equals 2q, big V for voltage, over m, square root. This will become equation 1, which we'll use in just a second. At the same time, I know that the magnetic force, for whatever reasons unknown, cannot apply a true, it can't make it actually change its energy. It can change direction, but it cannot change the energy of the system. So let's save equation 1 down here. Move this stuff out of the way. Because it can't change the energy of the system, this is going to be true even if the particle has changed direction. Okay? Now I'm going to take the Lorentz force that we already talked about and leave out that little part about the electric potential. I know that in this case, that means that force equals Q velocity cross magnetic field. But based on this drawing, you should be able to see that V cross B simplifies, because that's really Q, velocity magnitude, B magnitude, times sine 90, which is 1. Not only that, but I know that this gives me a centripetal force, meaning I can replace F with ma, with A being V squared over R. So that's m V squared over R equals Q B B. Now it's all good because I can get rid of 1V. Let me write this again. That's m V over R equals QB, where V is something I already know by equation 1. So by combining 1 and 2, then I get m over R times square root of 2q voltage over m equals QB. We're almost there, so hold on. This is all good except that I've got that silly little square root sign in there. So what I'm going to do is I'm going to take a square of both sides of the equation. Okay, that gives me m squared over r squared times 2q, v for voltage, over m equals QB. Q squared, B squared. Now, I'm going to cancel some good things out. M's go away, Q's go away, leaving 1 of each. And I'm left with 2V over R squared equals Q over M. Bring the B squared to the other side. And we're done. As long as I know the voltage that I accelerated at, the radius of the particle's movement, which we can measure, and the B field